Hey everyone, so today we're going to be fighting the final exam of spring 2007. In this first problem, we have a small bead P is moving along a part of the wire that is inclined at a fixed angle theta, this part here, relative to the horizontal plane, relative to here. The wire rotates at constant rate omega about a vertical axis relative to the relative to the ground. Find nice expressions for the velocity and acceleration of point P relative to the ground. First of all, I'm going to create my ground frame because it wants things relative to the ground. So this is a frame fixed in the ground. I'm going to call this the E frame and denote this as E1 hat, this as E2 hat, and then E3 hat points out of the page by right hand rule, right? If we curl our fingers of our right hand from E1 to E2, our thumb should be pointing in the direction of E3. So, yeah. Now we want to know how our system is moving. So our system is really just a rigid wire, right? That's rotating around the vertical axis. And it's rigid because we are given that the part of the wire that is inclined, so this part, is inclined at fixed angle theta relative to the horizontal. So it's always fixed at this angle, which means that it's essentially behaves as a rigid body. So we know that there is one rotation in the system, which is the rotation of the wire, and thus we need to establish a reference frame for a reference frame fixed in the wire. There are two ways to do this. I will show both ways because I think it's good to know how, even though you can have different reference frames, like orientation, you should still get the same answer, and it's a good way to check your work. So the first way, if I create a reference frame fixed in the wire, I can fix it in the vertical part of the wire. So maybe my reference frame, which I'm going to call the A frame, looks like this, where A1 hat is in this direction, A2 hat is in this direction, and A3 hat is in this direction. I could alternatively create a frame that's fixed in this part of the wire instead of the A frame. And this, maybe I could have the B1 hat point in this direction, B2 hat point in this direction, and then B3 hat points in the same direction as A3 hat then by right hand rule. So there are two methods to do this problem. The first method is using the A frame. The second method is using the B frame. The fundamental methods for solving the problem are the same. You just use different reference frames, and that's where potential confusion can come in. But I will do both ways so that we can see how to do it. The first method, which is method 1. Okay, so the question is, how do we find the velocity and acceleration? Well, we know that the velocity of point P with respect to the ground frame, so the E frame, is equal to the time derivative with respect to the E frame of the position vector from point O to the point of interest, or point P. Point O is a point fixed in the E frame, which is always going to be the frame you're differentiating with respect to. So in this case, it is the E frame. And so first we need to figure out what our point O is, a point that is fixed in the E frame. And this goes for both methods, right? Because a method is to take the differential, or differentiate the position to get velocity, and then differentiate acceleration to get, or differentiate velocity to get acceleration. So we always need to choose for our position vector a point that is fixed in the E frame. So what is a point that's fixed in the E frame? Well, obviously this point is going to be fixed here. This point is also fixed, right, because it's just a point that I choose on the wire, and since this wire is rotating about this axis, the points on that wire are not going to be moving. So the points like from here, 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 here are all not moving. However, don't choose like a point here, because that point is obviously that point on the wire is going to be moving with respect to the E frame, right? So that's something you wouldn't want to pick. But an easy point to pick would be here, because if I pick that to be point O, then my position vector from O to P, I should do this in blue, is actually equal to x in terms of the A frame. I would go a distance x cosine theta along the a1 hat direction and x sine theta in the a2 hat direction. So let me write that out. Equals x cosine theta a1 hat plus x sine theta a2 hat. So this is an expression for r to o to p in terms of the A-frame. I don't remember if I said this. So basically point O is fixed in the frame because this point is not moving. It's not along this part of the wire, which would be rotating around, spinning around, and moving with respect to the E-frame. But any point along this part is not moving because the wire is rotating about this axis, so the points on there are not moving relative to the E-frame. Okay, now that we know that, we can find velocity of P and E, which is the time derivative of this expression. So using BKE, we know that the time derivative is then first the time derivative of the expression with respect to the frame it is currently written in, which is the A-frame, right? This is written in terms of the A-frame unit vectors. Then we add the angular velocity of the frame it's written in, the A-frame, with respect to the frame we're differentiating with respect to, which is the E-frame. That, take the cross product with the original vector, which is this. Okay, so let's evaluate this first term. This first term, we know that theta is a constant, so that means that cosine theta and sine theta are constants, but the speed is told to be moving along the portion of the wire that is inclined. So P is like moving along here. So this means that the distance x is changing. So we cannot assume that x dot is 0. So this becomes x dot cosine theta a1 hat plus x dot sine theta a2 hat. Okay, that's the first term. Now the second term is the angular velocity of A with respect to the E-frame. So in this case, the angular velocity is around here, right? So if we curl our fingers in the direction of omega, our thumb points in the direction of the angular, if we curl our fingers in the direction of the angular rotation, our thumb should point in the direction of the angular velocity. So your thumb, based on this, should be pointing, of your right hand, should be pointing the A2 hat direction. So the angular velocity is omega A2 hat crossed with the original vector, which is x cosine theta A1 hat plus. Okay, this gives us, I'm just going to copy. I do wonder if it just takes the same amount of time to copy and paste rather than just rewrite it. But anyways, so A2 hat cross A1 hat gives us negative A3 hat. So we get x omega cosine theta A3 hat negative, right? Yeah. And then A2 hat cross A2 hat is just 0. So we are Gucci. So this is our expression for the velocity of P and E. Okay. And then I'm going to do the same for the second method. And I'm not gonna, I guess, actually it's fine, yeah. Okay, actually, yeah, I can find acceleration for this too. It's not too bad. So if I were to find now the acceleration of P and E, that's equal to the time derivative of the velocity of P with respect to the E-frame. This is then equal, apply the BKE again. We take the time derivative of this expression with respect to the frame it's currently written in, which is the A-frame. So what is that? That is equal to x double dot cosine theta, right? Cosine, or theta is constant, so we don't, that cosine theta becomes a constant, plus x double dot sine theta, same thing with sine theta, minus x omega cosine theta. From the problem statement, the omega is constant. And so we just have minus x dot omega cosine theta a3 hat. That is a time derivative of the velocity with respect to the frame it's written in, or the A-frame. Then we do the same thing where we add the angular velocity of A and E crossed with the original vector. Okay, so this becomes this plus, so the angular velocity of A with respect to the E frame is just omega A2 hat, right? Cross with VPE, which is this. Cross with x dot cosine theta. Yep. So this becomes A2 cross A1 is negative A3 hat, so we have negative x dot omega cosine theta A3 hat. A2 hat cross A2 hat gives you 0, and then A2 hat cross A3 hat gives you A1 hat. Yeah, so we get our final expression is going to be this. And we can recombine terms to make it look nicer. And this is our final expression for the acceleration of P and E. Okay, so this is cool, but we can check our work with the second method, which is using the B frame. So, this will be, yeah, okay. Using the B frame, what is our position vector? So in this case, our position vector is just a distance x along the B1 hat direction, right? This distance in the B1 hat direction. So we have x B1 hat. And then using BKE, we can write this as x dot B1 hat, which is a time derivative with respect to the frame it's written in, which is the B frame, plus the angular velocity of the B frame with respect to the E frame crossed with, sorry, my brain just went blank, crossed the original vector, which is x B1 hat. So the question is, what is the angular velocity of the B frame with respect to the E frame? So this is kind of weird because this B frame, if you kind of visualize it spinning, it's kind of like spinning around. So this is the B frame, right? It's kind of spinning around this like axis, so it's kind of like swiveling around, you know? I think maybe think about it and try to visualize how it looks. But I mean, even from just this diagram, you can tell that the angular velocity, right, as we said for the first method, points in the direction of A2 hat, right, based on right-hand rule. So we can then also say that the angular velocity of B and E is in the A2 hat direction with the angular velocity of capital omega. This is because the B frame is rotating at an angular speed of omega, but around this axis, which we cannot really write too easily in terms of the B frame right now. So this is why we can just write it in terms of another frame, but the fundamental rotation is still true to the B frame. So what does this mean? First of all, an issue is we cannot cross product the A frame with the B frame. They have to be in the same frame. So let's try to write the A2 hat unit vector in terms of the B frame. So the A2 hat unit vector is in this direction, right? This is the direction of angular velocity. And we also know that A2 hat always points in this direction, right? Because if it's fixed in the wire is always rotating around the A2 hat axis. So A2 hat always points in that direction. And then we also know from the geometry of the problem that B1 hat is always at an angle theta relative to A1 hat. So we can rewrite this then. We can write the geometry now as this angle is 90 minus theta. So this angle is theta. So A2 hat is equal to, we go this way along the B2 hat axis or unit vector, and that's a distance of cosine theta, right, adjacent. And then we go a distance along the B1 hat, a distance of sine theta in the B1 hat direction. So we can now write our B2 hat, or A2 hat, as omega cosine theta in the B2 hat direction plus sine theta B1 hat. Cosine theta, sine theta B1. Yep. Okay. And now we can just do our cross product and we get, so we'd have this omega cosine theta B2 hat so B2 hat cross B1 hat gives us negative B3 hat, and then we have B1 hat cross B1 hat, which is just 0. So this is our final expression for the velocity of point P with respect to the E frame. Okay, let's compare that to the expression we got up here. So we have, so notice first, let's just compare terms. So the A3 hat and the B3 hat vector point in the same direction. We did this, remember from our frames, we had defined them in such a way that they point in the same direction. The only difference between the A frame and the B frame is that they're tilted. So this term matches. So this B3 hat and A3 hat term match. Now we can look at the x dot term. So we notice that this is written as B1 hat, but this x dot term is comprised of A1 and A2 hat. However, we just realized from this vector projection that we can write the A frame in terms of the B frame. So let's see what B1 hat is equivalent to. And if you do that, B1 hat here is equal to cosine theta along the A1 hat unit vector plus sine theta along the A2 hat unit vector, which is exactly what you have here. So this means that our expressions do match. This matches, let's use a different highlighter. So this term matches with this term. And you can determine that just based on vector projection, observing how the B frame and A frame are related to each other. So that is our velocity, and now we can do the same thing for acceleration. It is really the same thing, because we just do BKE again. So first, I take the derivative with respect to the frame it's already written in, which is the B frame. So this becomes x double dot B1 hat minus x dot omega cosine theta. Cosine theta and omega are constant as stated in the problem. Then we do plus angular velocity of b cross, with respect to the e-frame cross with the original vector, which is this. Okay, this gives us x double dot plus, now the angular velocity of b is equal to this. So this cross with this becomes, so let's do the determinant method just for my own sanity. b1 hat, b2 hat, b3 hat. So the first term is the omega b of e, which is equal to this. So this is equal to omega sine theta, omega cosine theta, 0, and then this is x dot 0 minus omega x cosine theta. This is the second term in the second row. So this gives us, if I cross out the first column, which is the b1 hat column, is equal to omega cosine theta times negative omega x cosine theta, which just becomes negative x omega squared cosine theta squared minus 0. And then we subtract from that 0 times 0, which is just 0. So that is our b1 hat term. Then we do the b2 hat term, but because it's the b2 hat term, you have to put a minus sign up front. So you have minus b2 hat times omega sine theta times negative omega cosine theta x, negative x omega squared cosine theta sine theta minus x dot times 0, which is just 0. Now the b3 hat, this one is normal, so we just have a plus b3 hat is equal to 0 times omega sine theta, which is 0, minus x dot omega cosine theta. So this is negative x dot omega cosine theta. Okay, and then we can simplify this, and this becomes x double dot minus x omega squared cosine squared theta b1 hat plus x omega squared cosine theta sine theta b2 hat plus minus x double or x dot omega cosine theta 2 minus 2x dot omega cosine theta b3 hat. And this is the acceleration of point P with respect to the E frame in terms of the B frame. Let me just check real quick with the answer key to make sure I'm on the right track. Yep, so this is correct. And now we can compare with the method 1. So let's look at that. It's a bit rough, I guess, to compare. But first of all, this term, A3 hat and B3 are in their same direction. So these two terms match, which means we're correct. And the other thing is that we would have to express the B1 and B2 hat unit vectors in terms of, like, say, the A-frame or the A-frame vectors in terms of the B-frame. And I think we can agree that based on our vector projections that if we have, let's see, how do we do this? I think it's pretty complicated either way, but we already established previously that B2 hat is equal to, we didn't actually establish this. But let's just say we're converting the B frame unit vectors to the A frame unit vectors. So I'm going to write then B2 hat is equal to, in terms of the A frame unit vectors, it is a distance negative sine theta, so negative sine theta in the A1 hat direction, plus cosine theta A2 hat. Right, we go this way and then we go this way. And using trig, we find the vector projection. So I think if I plug that in down here, it would give me the answer. I'll just do that really quick. I think you can verify for yourself. It's just a plug and chug at this point. So x double dot minus. This is completely unnecessary also as a part of the problem, but it's just like helps you get familiar with these things. So times cosine theta 1 hat plus and then oh wait, yeah, and then this becomes B2 hat is negative sine theta A1 hat and then plus cosine theta okay, that's ugly. Did I do that correctly? So B1 hat is cosine theta A1 hat plus sine theta A2 hat. And then this term is negative sine theta. Is cosine theta A2. Okay, yeah, so these are correct. And I think if we group the terms now, so if I group the A1 and A2 hat terms, we get x double dot cosine theta. So, this is, so minus x cosine cubed wait, sorry. Oh yeah, okay, sorry. So we're good. So we can use factoring. So we can minus cosine theta x omega squared cosine squared theta plus x omega squared sine squared theta. Using trig identities, we know that cosine squared theta plus sine squared theta is equal to 1. Right, we can factor out the x omega squared and then get this, and then this just becomes 1. And then for the x2 hat term, we have x double dot sine theta minus sine theta sine theta x times x omega squared cosine squared theta. Oh wait, this just cancels. So this term and this term cancel each other out. Do they do that? Yes, they do. And then we are just left with x double dot sine theta A2 hat. So when we compare then up here, we see that the x double dot sine theta A2 hat matches with this, and the x double dot cosine theta minus x omega squared cosine theta A1 hat matches with this. So overall, both methods work. It just is a matter of which one you maybe think of in the moment. But you just apply BKE to both, and you should get the same answer for both if you write it all in this terms of the same frame, as we have demonstrated. I think the key thing to note in this problem is that the angular velocity of B with respect to the E frame is equal to this rotation. The B frame is rotating, but is rotating with an angular velocity in this direction, which is the key thing to note about this problem. And when you do that, you have to write it in terms of the same frame as the B frame and blah, blah, blah. So you just do the math there. But this is the key thing to observe in the problem. Even though the B frame is tilted, its angular velocity is still in the same direction as the A-frame. So now we can go to problem 2. We don't have a lot of room, so let me just actually move. Let's do this. Okay, problem 2. A small ball of mass m equals 0.1 kilograms is attached to point A via a string and is moving at constant speed in a horizontal circle of radius r, which is 0.16 meters. So we know that m is equal to 0.1 kilograms, r is equal to 0.16 meters. The rate of rotation of the ball around the circle, so this omega here, is equal to 2 radians per second. And g, the gravitational acceleration constant, is 12 meters per second squared. Okay, and then it's asking for the value of height d, which honestly, at first glance, seems kind of like, what, So I'm not too sure what to do, but I know, in our toolbox that we've learned, how to find the acceleration of this mass and also the forces on this mass, right? So maybe we just try something and hope it works, because we should be able to figure that from the equations we get using, F equals ma, or the acceleration of the ball or velocity. So I'm going to do F equals ma because that gives me equations and maybe I can figure out something from that equation. So we know that sum of forces equals mass times acceleration. Now, what are the forces acting on this ball? So first of all, I'm going to actually pause for a second and just say we need to create frames. I should have said that first. But we should introduce frames first because we need to know what we're considering acceleration and stuff with respect to. So I'm going to create first a ground frame. So I'm going to call it the E frame. And this is the E1 hat vector, E2 hat unit vector, E3 hat this way. And then I'm going to create a frame that is rotating with this ball. And all that means is I'm just creating a frame that follows the ball that is fixed in, something here maybe, that follows the ball as it rotates around the circle. So I'm going to create a frame. There's only one rotation going on, right? As it's you can think of it as forgetting about the forces for a second. It's just a particle moving in this. So how can I describe the motion? Like we've previously done in the class, we create a reference frame. So I'm going to create a reference frame that is pointing, one of the unit vectors points towards the ball. This is the B1 hat. I'm going to call it unit vector. And then I'm going to call this the B2 hat unit vector. And based on right-hand rule, B3 hat points into the page. And yeah, so this is just in this instance. So the B vector is fixed in this part here, but it is rotating with mass m about the B2 hat axis. So now that I've established my axis, I'm going to draw my free body diagram. So first of all, the free body diagram will be in terms of this B frame. So I have it this way. And why do I want to draw it in terms of the B frame? Well, if I did it in terms of the E frame, notice that if my ball is here, right, the forces I have on this ball is this force of the string and then the gravity. So gravity obviously always points down, that's fine, but the tension is going to point in different directions based on wherever, I am in this ball's trajectory. So if I write it in terms of the B frame, which is always rotating with the ball, then I will always have an easy way of writing the tension of the string. So I'll just demonstrate that in a minute. So what force is acting on the ball? We have gravity, of course, acting always in the downward direction. And then we also have tension, which is in this case acting in this direction in terms of the B frame. By writing in terms of the B frame, we account for the fact that the ball is rotating around and the tension points in different directions to someone standing in the ground frame, in the E frame. So we have a tension force in this direction. And let's just say it's at some angle theta, because we're not really told in the problem, so we just make up some variable to figure out what the angle is at. And actually, I'm going to do this as theta. Okay. Just to reiterate, I don't know if I explained that very well. We first create our frames, right? And we choose to draw our free body diagram in terms of the B-frame, because the B-frame is rotating with the mass. And so in terms of the B-frame, tension is always pointing in this direction. But of course, if someone's standing in the E-frame, they observe the ball as having tension force on it in this direction or this direction or this direction. But because we have written this in terms of the B-frame, that already accounts for the rotation of the ball, because the B-frame is rotating with the ball. So then we were able to write our force much more easily, instead of having to do some funky 3D stuff and trying to draw the tension force this way, in terms of the E-frame. So anyways, then this means that our sum of forces is equal to the force of tension plus the force from gravity, which is then equal to tension is acting in the negative b1 hat, negative cosine theta b1 hat direction. So we have, maybe I should do this. So tension is equal to the magnitude of the tension force times cosine theta in the negative b1 hat direction. And then we go up in the b2 hat direction. So we have plus t sine theta b2 hat. And then we have our gravity force, which is always pointing down. So it's pointing in the negative mg b2 hat direction, right? B2 hat always points this way because the rotation is about that axis. So it doesn't matter. We could have also written this as negative mg e2 hat, because b2 hat and e2 hat point in the same direction since they always point up. This means that our sum of forces is then negative t cosine theta b1 hat plus t sine theta minus mg e2 hat. Okay. Now we can figure out what ma is. So what is the acceleration? We want to find the acceleration of the ball with respect to the E-frame, because our force is our perspective of what the forces are acting on the ball from the E-frame. We have just expressed it in terms of the B-frame. So the acceleration of the ball, of the point P with respect to the E-frame. Oh, I'm so sorry. I think I was just referring to it as P. I'm referring to P as this point, the mass of the ball. Or not the mass of the ball. The ball is point P. So sorry about that confusion. So anyways, we find the acceleration of point P with respect to the E-frame. And this is where acceleration expansion comes in handy. So let me actually, I kind of don't remember what acceleration expansion is, or what the formula is. Give me 1 second. So the acceleration expansion is equal to the acceleration of some point that is not moving in the frame that is rotating. So in this case, I'm just going to call some point B that is not rotating with respect to the ground frame, or not rotating with respect to the B frame, but we find the acceleration of that point with respect to the E frame and the acceleration expansion equation. So that was extremely poorly explained. So B is just a point fixed in the B frame. And then we plus the angular acceleration of that frame, so the B frame, with respect to the E frame, cross with the position vector from point B to P, and then we add to omega of B and E, cross with the velocity of point P with respect to the B frame, plus, this is extremely long. And honestly, if you knew the expression for just centripetal acceleration, you could just plug that directly in. But I'm just showing how you would get it if, say, the acceleration was more complicated. Okay, so first of all, notice that the problem says that the ball is moving at constant speed, and also the angular rate of rotation is given to be a constant, which is 2 radians per second. So this means that omega of B and E, right, which is equal to, okay, sorry, I should calm down. So the angular velocity of B with respect to the E frame is equal to, we curl our fingers in the direction of the rotation of the B frame, which is in this direction, and our thumb points in the direction of the angular velocity. So my thumb right now is then pointing in the B2 hat direction. So this is equal to omega B2 hat. And that's going to be a constant, right? Because omega is a constant. So this means that the angular acceleration is equal to 0. Now we look at some other terms. So the velocity of point P in the B frame. So the B frame is rotating with point P, right? And there's no mention of point P like moving in this direction or in like any other direction. It's just going around in this like horizontal circle. There's as stated in the problem. So it's just this flat circle. So the B frame is rotating along with point P. So in the B frame, to someone standing in the B frame rotating around like this, point P is not moving. Thus, the velocity of P with respect to the B frame is equal to 0. So this term becomes 0. And the acceleration of point P with respect to the B frame is also 0. So that's quite nice. And then we realize that also a point then that is fixed in the, let's say a point that is easy to find a point that is fixed in the B frame, which is pretty easy to find, is, let's say point O. Point O is a point that is fixed in the B frame, right? It's just the center of it, so it's not moving. So the acceleration of point B with respect to the E frame is actually 0, right? This point is always going to be, stationary here, even to someone standing here. It is the center of the B frame, but it's not like translating or it's not rotating about anything. So this term then also becomes 0. So let's say that this expression, we have simplified it already to this. And this has been determined to be 0 because of the point we chose, which is O. And we just chose point O because, right, it's really easy to figure out what, the velocity, we know it's a point that is stationary in the B frame. And it just is also very convenient because we can eliminate this term. So really our expression is just this. So this becomes omega B2 hat crossed with omega B2 hat crossed with ROP. So the distance from O to P is going to be a distance, or not a distance, or it is a distance, but it's going to be R along the B1 hat vector. Okay, this gives us omega B2 hat crossed with omega R B3 hat negative omega R B3 hat, which equals B1 hat, negative omega squared R B1 hat. And this makes sense, right? Because like centripetal acceleration is for a situation like this where you have just a simple circular rotation in a plane. It's always going to be pointing inwards for the circle, so it will be pointing in the negative B1 hat direction. So this makes sense to us. So we can go back to our F equals ma. So we first found help. How do I? Okay, I don't know what that was. So we have, first we found the sum of forces, then we found the acceleration. We can put it together now, and we can see that negative t cosine theta b1 hat plus t sine theta minus mg a2 hat. Did I write e2 hat? My bad. It should be a. Or not, it shouldn't be a, it should be b. So sorry. B2 hat. Why am I writing A2 hat? Okay, B2 hat. equals mass times acceleration. Acceleration is just this, so it equals to negative m omega squared r b1 hat. And then if I look at the components in each of their respective directions, I have that negative t cosine theta equals negative m omega squared r. And then in the b2 hat direction, I have t sine theta minus mg equals 0. And then you're like, okay, this is all pretty useless so far, it seems. But then it's asking for the height d. So we know from this really messy drawing, which I'm going to clean up real quick. So this is, I wish I wouldn't put the r right there, but it's okay. So, okay, I'm going to draw B1 hat as pointing over here now, just so we can like actually see the r. But r is the radius, right? And so to figure out what d is, we can take advantage of this theta that we've defined, and we recognize that this theta, and we can just kind of look at this and be like, oh, we're given what r is. Can we use this information to write theta in terms of d? So a key step here to note is that tangent of theta is equal to d over r. But to be honest, even if you didn't realize that, you could just recognize that, cosine theta, in this case, cosine theta, is equal to r over d squared plus r squared, all square rooted. But that's just kind of a complicated expression, and I think solving it might be a bit painful, so we would probably prefer to stick with this tangent theta stuff. So looking at these expressions now, we're like, oh my gosh, tangent of theta is equal to sine theta over cosine theta. And we can then take advantage of these quantities that we know, which are like g, m, r, omega, and we can then solve for d. So I'm going to write these two expressions then become t cosine theta equals m omega squared r, t sine theta equals mg, and then I can divide this expression by this expression. So take this, divide by t cosine theta. So I have not read a division sign like that in a very long time. So this becomes tangent of theta. We didn't really need to know what tension was after all. And then mg over t cosine theta, we know that t cosine theta equals this, so we have mg over m omega squared r, which just gives us g over omega squared r. And then we're like, tangent of theta is equal to d over r. So we can write this as d over r equals g over omega squared r. We didn't really need to know r after all, so we have g over omega squared, which is in this case 12 meters per second squared over, it's 2 radians per second squared, which is just 12 over 4, which is equal to 3 meters. Radians are unitless. And this is our expression for d, or the answer for d. And again, this is just found by just, trying something that seems like it could work. So F equals ma, something we learned in this class. When we did F equals ma, we expressed it in terms of the B frame for simplicity. And then we found the acceleration of point P with respect to the E frame using the acceleration expansion. You could also have done this in terms of the BKE. If you took the derivative of the position vector from O to P, you would pick point O because it's fixed in the E frame. Then you would take the derivative with respect to the E frame and just do BKE to get velocity, then do BKE again to get acceleration. It's a similar process to this. It's perhaps a bit simpler, but yeah. And then we just figure out the equations, and then we look at the trigonometry and the geometry of the problem. And we notice that tangent of theta is equal to d over r. We express that in terms of, so we expressed, these equations in terms of d, and then we were able to solve for it. Okay, problem 3. Find the moment of the force F of magnitude 10 pounds above point, or about point O. This is point O. And the force is, acting along this line. So this, I think it's called line of action. But yeah. Okay, so the first thing to do is we see this probably calls for vectors because force is pointing in a direction that's like crooked, right? It's along the hypotenuse of this triangle. And so let's create a reference frame first so that we can at least write things in terms of unit vectors. So I'm going to create the E frame. I'm going to say that this direction is equal to the E1 hat unit vector and this direction is equal to the E2 hat unit vector. And then this is, so it's kind of like this kind of thing, going on. So then this direction is the E3 hat, right? It points out of the page. But in this case, it's a 3D drawing, so it looks like that. So that looks kind of weird. Okay, I should do this. Okay. So how do we find the moment? Well, we know that the moment about a certain point, so in this case, they want it to be about point O, is equal to the sum of the lever arm, so the position vector, from the point O to some point, let's say AI. So these are different particles in the system, crossed with the force acting at that location. So in this case, we really just have one force, so we would just have R from O to the point that it is force is acting at, crossed with F. Okay, so the question first of all is, what is this position vector and what is point A? So A is just a point that this force is like stemming from, I guess you can think of. So the thing is, it could be from along any point along this line. So it could be here, here, or here, whatever. I think an analogy that is helpful to think about is that if you have a door, let's say, and you're trying to, you're pulling this way, so perpendicular to the door, and let's like just draw a coordinate system. We have X, Y, Z. You're pulling along this direction in the Y direction with some force, and you're trying to find a moment like about the hinge, let's say, of the door. Well, it doesn't matter if you are considering the lever arm as being from here to here, or here to here, or here to here. It just has to be along this force line of action. And this is because when you take the cross product, you're just finding the vector that is perpendicular to the vector that is perpendicular to R and F, right? That's like kind of how the cross product is. You can think of the cross product. So the moment really only cares about the part of the lever arm that is perpendicular to the force. And thus, no matter where you go along this line, the perpendicular component is always the same. It's just this like longitudinal component that changes. But that gets canceled out in the expression for moment because moment only considers the perpendicular direction to force. So that's why you can choose any point along this line of action. And that's why here we apply that same idea. So, you can choose here, and I'll actually just demonstrate that they're the same. So I'm going to say this is point A and this is point B. But yeah, so let's just do with point A first. So what is the vector from O to A? I should do different colors for this like I did problem 1. Actually, that would be nice. So I just keep it like, just do some like other point. Okay, so if I use point A, the expression for moment about point O becomes the position vector from O to A crossed with the force. So what is the position vector from O to A? Well, you go distance 4 feet in the E1 hat direction, and then you go up a distance 2 feet in the e2 hat direction. So this becomes, so 4 feet in this direction, e1 hat plus 2 e2 hat crossed with force. So what is force? Well, it has magnitude 10 pounds and it's in this direction. So we cannot just like say that it's 3 in the e3 hat direction and 4 in the e1 hat direction. So we need to remember how vectors work. So vectors are always equal to their magnitude times the unit vector, which is a vector that has magnitude 1 but points in the direction that the force vector is pointing in. So in this case, our unit vector is in this direction, right? So we're going to have u be equal to, so this equals 10 pounds times u, right? It's magnitude 10 pounds. And the unit vector is in this direction. So how do I find the unit vector? First, I just find like a vector that is in the same general direction as u. So one vector that is in the same general direction as u is, let's say, this vector from B to A. And what you do is you take that vector and you divide it by its magnitude, because the unit vector has magnitude 1. So this gives us, let's see, so if B to A is 3 feet in the E3 hat direction, and then 4 feet in the E1 hat direction. So we have 3 E3 hat plus 4 E1 hat divided by the magnitude, which is equal to 3 squared plus 4 squared. You add all the components up in quadrature. So you square them basically and add them together. And then you take the square root. And based on the 3, 4, 5, right triangle, you get that 3 squared plus 4 squared over, or 3 squared plus 4 squared square rooted gives you 5. So E3 hat plus 4/5 E1 hat. Okay, this is a unit vector, and notice how this has magnitude 1. If I found the magnitude of u hat, it's 3/5 squared plus 4/5 squared, which would give me 25 over 25, and then you square root that, and that is 1. So this makes sense, right? This is a good check that it is magnitude 1, and it is in the same direction as the force vector, right? It is in this direction. So I can plug that back in up here, and this gives me that force equals 10 pounds times 3/5 E3 hat plus 4/5 E1 hat. This is in feet because it's like a 1 dash thing, so it's in feet. This then just simplifies out to 6 foot-pounds E3 hat plus 8 foot-pounds E1 hat. And then I put that in here, so 6. I'm going to leave out the units for now, but let's just like keep them in mind when we find our final answer. So this gives me, I'm going to do a determinant method again, E1, E2, 3. So this first term becomes 4, 2, 0. This one becomes 6, 8, 0. And then when I do the determinant stuff, I get 12 E1 hat minus 24 E2 hat. Right, so I take this column, I use 2 times 6 minus 0, which is 12. Then I subtract E2 hat because it's special. E4 times 6 minus 8 times 0. And then the same thing with the last column, but this one's normal again, so it's a plus. And then it's 0 times 4 minus 8 times 2, which is 16. So yeah, that's fine and dandy. So we have now the moment about point O. And this is in terms of, based on units, foot, pounds, foot squared pounds? I think that is, yeah, that would make sense. Wait, no. Wait, what? Oh, wait, sorry. What am I doing? I'm so sorry. So this is actually unitless. I don't know what I was thinking. So the unit vector is just a like direction. It doesn't have a unit to it, right? Because we made it have magnitude 1 by dividing it by its magnitude. So this would have units of feet, and this would have units of feet. And this gives us feet over feet. It just cancels the dimension. So we have this being dimensionless. So this is actually just pounds. And yeah, anyways, sorry about that. So this is all just pounds, and this is just pounds, and this is in feet. So then when you multiply them together, you get foot-pounds. And this is the moment about point O. This is found by choosing our lever arm to be from O to A. But B is also on the line of action, so we can also do the same thing there. So let's try it with B just for practice, like just so we can get comfortable with the different ideas, different ways you can pick your point. So if I pick point O, or point B, my moment about point O is equal to R OB crossed with force. And we already said, so force stay the same. Force is just a vector. It doesn't matter where your lever arm, you choose your lever arm to end at. So we have ROB crossed with 6E3 hat plus 8E1 hat. Okay. So what is ROB? Well, you go from O to here, and you go from there to there. So you go a distance 3 feet along the negative E3 hat direction, and then you go a distance 2 feet in the E2 hat direction. So we go negative 3 E3 hat plus 2 E2 hat cross with 6 E3 hat plus 8 E1 hat. And then we can also do the determinant again. Negative 3, 2, 0, 8, 0, 6. All right, this gives us 12 E1 hat plus negative 24 E2 hat, and then minus 16 E3 hat foot-pounds. And notice that this is equal to this. So these two different ways give you the same result as long as you choose a point that is on this line of action of the force. So yeah, that is this problem. Okay, last problem. This massless structure supports a block of weight W equals 100 pounds. And find the tension in the cable at B, so this is a string then, and the reaction on the structure at support A. Okay, so let's first create a coordinate system so we can just make sure we can write things in vector form. So I'm going to create, again, my favorite E1 hat, E2 hat, and E3 hat unit vector, and this is just affixed in the earth. And we notice that this entire contraption is in static equilibrium, right? It supports a block, and so we know that when we do, for example, F equals ma, this entire thing should not be moving with respect, to the fixed ground frame. So that is that, and then we also know that the sum of moments should be equal to 0. Because no structure here is like rotating, right? Everything is not moving. It's being supported. Okay. So we want to find the tension at cable B. So some force acting here, and also the reaction on the structure at support A. So this pin here. So let's just also identify some things in the problem. So this is a pin. This is also a pin because they're usually identified just by like something like this. You will learn this more in 204. And then this is a roller. Okay. And the properties of a pin are that they exert, a force in some direction, like this kind of thing. So you can decompose this into two reaction forces. So one, say, in this direction, in the E1 hat direction, and one in the E2 hat direction. And then for rollers, so let me just do this actually. I think this will make it easier. So if I have a pin here, and that means it's exerting a force in this direction or in this direction. You can just pick the directions arbitrarily. You can also pick like this direction or this direction. But just know that it has some force in the this planar direction. So why did it do that? So this means that these pins will have that kind of behavior. It will exert a force, but it will exert no moments at that point. And then the roller, so I have a roller here. It will exert a force tangential to the surface. So in this case, the roller would exert some force in this or this direction. Unlike the pin, which exerts a force in the planar within the plane, and there's no single direction it must exert a force in. Okay, so that's just a little bit about pins and rollers. Now, to figure out the reaction forces, this is kind of complicated setup. So the way to solve this is to break it down into the two different bars you can think of. So for in this case, notice that I have this bar, A, B, C, and then I have a second bar, which is B to D. So whenever you have something like this, it's always a good idea to draw stuff in terms of the bars or the things that have the pins in them and stuff. So let's decompose this first. So let's draw our free body diagrams. We know that we can solve this question using these two expressions. So the first thing is this thing right here. So point A is here, point B is here, and point C, I guess, is here. Okay, what are the forces acting on this bar? So first of all, we have the pin force, right? The pin exerts some force, maybe in this direction, who knows? We can decompose that force into a reaction force from A in the E1 hat direction, right? Let's draw our frame here. E1 hat. You should always draw your frame with the free body diagram. And then we also have some force in this direction, in the orthogonal direction. So RA1, RA2. And then we have at point B, there's this string thing. So this is probably holding this bar up. So I'm just going to draw it in this direction, but we know that this string is exerting some force in this direction. So we have B, I'm going to call this TB. And then at C, we have a roller. So this roller, I know that it exerts some force in this tangential direction. So I'm just going to say it exerts a force this way. And that is all of the forces here. And I think it says this is a massless structure, so we don't consider the weight of the actual, this stick thing, ABC. And then some other things to note, this is at a 60-degree angle. So we have 60 degrees. The distance from A to B is 6 feet, as given here. Okay, that is our first free body diagram, and we can immediately just write our sum of forces and sum of moments. So what is our force summation? So we have in the E2 hat direction, we have RA2 plus TB plus RC, E2 hat. In the E1 hat direction, we have RA1 hat, or RA1 E1 hat. And this is all equal to 0, right? Because there is no acceleration, nothing is moving. This means that RA2 plus TB plus RC equals 0. And this also means that RA1 is equal to 0. This is in the E2 hat direction. This is in the E1 hat direction. So we know that the reaction in the E1 hat direction at support A is equal to 0. Okay, now we need to figure out what these other ones are. But, you know, we clearly don't know that yet. So let's just move on. And we can then figure out maybe moments, but I'm actually going to wait on that because like I feel like we could get more information using the second bar. So let's just do that first and then we can come back and look at moments. So in the second bar, we have point D here, we have point C here, and then we have some weight that is here. So these are the only forces acting on this specific bar. Right, this string is acting on the first bar, so we don't really consider it in this expression. So this is at a distance of 1 foot from that end, and this is a distance of 2 feet from that end. And yeah, so the question is, what can be confusing is you can be like, oh, maybe we should do a free body diagram of this weight. Well, that's honestly kind of like useless because this box is just like you can think of as sitting on some like surface. So then, you know, then we know the standard, there's some normal force acting up and then weight acting down. And we already know what weight is, so normal force is equal to weight, which gives us no new information. So we don't want to consider the free body diagram of the box. We want to consider of the bar. So let's just look at the bar and it's as just one thing. So we have the E1 hat, 2 hat, E3 hat. Okay, so what forces are acting on this thing? So we have the weight from the box acting at this point here. And it's acting at a distance 1 foot from here and 1 foot and 2 feet from here. And then we have this pin that's acting at D. So I'm going to draw this reaction force from D in the E2 hat direction plus reaction force from D in the E1 hat direction. And at point C, we had the roller, right? So this is where you have to be very careful. So in the first free body diagram, we said that the force that the roller exerts on the bottom, sorry, my brain just went empty. So the force that is exerted on the, why did it just erase? Okay. The force that is exerted on point C by the roller is in the upwards direction. But every action has a equal and opposite reaction, right? So the forces must cancel each other at this point. This means that the reaction force at C should be in the downwards direction for the top bar. If, for example, like if I had some structure like this, and there was a pin like here, then on this top bar, bar A, I would have, let's say I write the reaction force as this on bar A. Then for bar B, I need to write that in the opposite direction because of Newton's third law, I think. Yeah, Newton's third law. So that is a really important thing to note in this problem. So we write that. Oh, and then for example, if I instead had A as being like, the reaction force being like this, you would need to draw the reaction force at B like this. It always needs to be in the opposite directions. So that's why at point C, because the roller is acting on both bars, it's going to have a force in the opposite direction. Because otherwise, if it had a force on both in the positive direction, then there should be some non-zero acceleration at that point. So at point C. Okay, so now we can draw or write the sum of forces. And we have RD1 in the E1 hat direction plus RD2 minus W minus RC E2 hat equals 0. So this means that RD1 is equal to 0 and RD2 minus W minus RC is equal to 0. Okay. So we need to find T and we need to find A or RA. So let's take a look at this expression and then this expression. So now we can start to apply moment stuff, right? Because we kind of need to. But how to do that? So let's look at the problem and think about how we can do this. So, okay, so let's take the sum of moments about, let's see. Yeah, let's take the moments about point D, actually. I think that would be helpful. So if we do that, we get sum of moments about point D. So why did I choose point D? Well, first of all, I was like, we don't really know what D2 is, and we also don't need to know what D2 is that importantly, because we can just use this, and once we solve for RC, we can plug that in here and get our TB and RA2 with some other moment stuff later. But we don't really need to know what D2 is. We could solve for it, but it's just kind of a hassle. So the sum of moments about point D is equal to the sum of the lever arm from D to the point of interest crossed with the force at that point of interest. So in this case, we just have this point and this point. So, and also everything is perpendicular, so we can just directly be like this distance times the force, magnitude, because they're perpendicular to each other. So we just do, then for this first one, we have weight times 2 feet. And the moment is going to be in this direction, which is the positive E3 hat direction. So I'm going to write this in the E3 hat. And then the same thing goes for this. This causes, in the RC reaction, it causes the rotation this way, which is also in the E3 hat direction. So that is going to be a distance of here, which is 3 feet, times RC, E3 hat. And this is equal to 0. So this means that 2W plus 3RC is equal to 0. And we are given W in the problem to be 100 pounds. This is 200 pounds plus 3 RC equals 0. So this means that the reaction force at C is equal to negative 200 over 3 pounds. And this negative sign, all it means is that we drew the reaction force this way, right? But that means that the actual reaction force is pointing this way. And then you might be like, oh wait, what? But we just argued that like it must be equal and opposite reaction forces, right? So this makes sense then, because in our above drawing, we had drawn RC as pointing this way. But because we had solved for RC to be negative, it means that RC is actually pointing this way. So it still makes sense because RC actually points in this direction and this RC actually points in this direction, those two forces are still equal and opposite in direction. So it still works out. That's all the negative sign is telling us, is that the direction is flipped. So now that we know what RC is, we can go back to our first part and we are like, oh, epic. We now have only 2 unknowns in this equation. So we get, maybe I should write this down here. So from this, we now know that RA2 plus TB plus RC. So RC is negative 200 over 3 pounds is equal to 0. So now we're like, how do we find RA2 and TB? So let's look at this. So we know that we need to use the moment equation still. So how can we use it most effectively? Well, if we use it here, it's like kind of, I don't know, it's pretty much not that helpful because, well, okay, actually I guess we could use it here. We can use the moment about point C, and that would just give us, moments from tension and R, which is useful. So honestly, did we even need to find, no, we did need to find RC. Okay, yeah, so never mind. we're good. But let's say I use this one. Then I get some summation of RA2 and TB equals 0 because the sum of moments is 0 about any point here. And thus you can solve for R in terms of TB or something, and then you can plug it back into this equation and get the expression for one of them, and you could solve. Alternatively, you could pick to take the moments about B. This is also valid because then you would get your sum of moments to be from RA2 or RC. And so you have RC, and so you can then solve for RA2. And then you can do the same thing at point A. So basically, in this case, you can choose whichever point to take the moments about, and life should be good. So I'm going to choose to take the moments about point C. I actually think that's probably the easiest. So if I take the moments about point C, I have the force from TB at a distance of, it tells you in the problem that distance from B to C is 1 foot. So I have TB acting at a distance here in this positive direction. So I'm going to have a moment in this direction about point C. So that is in the negative E3 hat direction because it's in the opposite direction of E3 hat. So we have 1 foot times TB in the negative E3 hat direction plus, so now we have to consider the moment due to point A about point C. So you can do, this whole the lever arm from C to point A, but it's the trick, or I guess a way to make it faster, is to just recognize that this is acting in this direction, and the perpendicular distance is just this horizontal distance from A to C. So from here to here. So we can just figure out what this horizontal distance is and then multiply it by RA2 because that means that this is perpendicular, this lever arm is perpendicular to the force acting at that point. So we don't have to do this whole cross product stuff. So this is a trick that's just easier to do in for example, this problem. If you looked at problem 3, it is definitely not as clear to do. So that's why I would recommend for those problems to use this formula. But then for something like this, you can just figure out what lever arm or forces are perpendicular at a point, perpendicular to each other. So we have RA, and we define this distance from A to C. So from the problem, we have this is 60 degrees. So a distance horizontally from A to B is just like the distance, like the legs of a triangle, right? So you have cosine of 60 times 6 is equal to this distance here. And so cosine of 60 is 1/2. So this is just equal to 3 feet. And then you have from B to C, which is 1 foot, as we already showed up here. So this means that the total distance from A to C in the horizontal direction, in this direction, in the E1 hat direction, is equal to 3 feet. So we can write times 3. And this then is acting in what direction? So we know that our A2 hat, we defined it as acting in this direction. So our moment's going to be in this direction, which is a negative E3 hat direction. This is equal to 0. Okay, I can't do math. This was supposed to be 4 because I forgot to add the 1. So this distance was supposed to be 3. Then you add the 1, so it's 4. 4 feet. So that gives me negative TB minus 4RA2 equals 0. So TB equals 4RA2. Yeah. And then we can put this expression and this expression together, and you get RA2 minus 4RA2 equals 200 over 3 pounds. And then you can solve for RA2, which is equal to negative 200 over 9 pounds. And then similarly, now we can solve for TB, because TB is equal to negative 4 times RA2, which is just going to be 800 over 9 pounds. So those are the magnitudes, or those are the coefficients to the expressions we had up here from our sum of forces. So we can actually write this tension in the cable as we had written that T equals T. So we had written that the tension in the cable is TB in the E2 hat direction. So tension in the cable is going to be 800 over 9 pounds E2 hat. And then for the reaction force at A, that is equal to the reaction force in the E1 hat direction, which we defined as RA1, plus the reaction force in the E2 hat direction, which we defined as RA2. This is equal to, right, RA we found was equal to 0 up here. And then, what? Okay. We found that RA was equal to 0, and then we have RA2 was equal to negative 200 over 9 pounds in the E2 hat direction. So these are our answers in vector form for the tension in the cable at B and the reaction on the structure at support A. So yeah, that is the final problem. And just to recap, what we did was we first we split up this complicated structure into the two bars, because those give us actually useful information about these forces that we're trying to find. When we do that, we draw our free body diagram. We know how pins and rollers behave, so we can draw the forces. The very important thing to note is that if you have a reaction force that's, like this, acting on two different bars at the same point, you're going to have to draw the reaction forces as equal and opposite in the two different free body diagrams. So in this case, on this free body diagram, we just represented the roller to be in the upwards direction, so we have to have it be in the downwards direction in this second bar to satisfy Newton's third law. And then what you do is you can do sum of forces, and then you might just have to think a little bit and look at the forces and consider what points should I take the moment about, because whichever one you choose to do will make it easiest on you to find the variables you need. So in this case, right, we decided to take the moment about point D because we don't really care about point D, but we are given point W and which we can use to find the reaction force at C. We, again, because it's a moment about point D, we don't consider the forces at point D. We don't consider the forces at point D because the lever arm is then 0, right? D to D is just 0. So we only get information about RC, and then we can solve for RC, which we can then use in this expression to find the moments of. And in this expression, it didn't really matter which one you took the moments of because you have two unknowns. So whichever point you picked would have given you the same results. So another key thing to know is that we could take a bit of a shortcut by recognizing that if we find the horizontal distance between 2 points, that is going to be perpendicular to the force, which is essentially what we want from moments, right? Moments are produced from when you have a lever arm perpendicular to a force, and that force is acting around some point. And so we can use that shortcut to just do multiplication instead of cross products and stuff, although the cross products would work. And then we use that to find the moments and then plug everything in, and we can get our final answer. So I always suggest to do the F equals MA stuff first and then do the moments, because then you can maybe think about what you need in the problem. But yeah, that was this exam, so good luck.